Hello and welcome to the Department of Geography at Swansea University's Canvas site for A-level geography students. This is the first of a few videos where we are going to look at climate change from the perspective of geographers, starting with looking at the physical scientific basis for how geographers understand the evidence for the way climate is changing on our planet today. My name is Mary Gajan and I'm a physical geography professor here at Swansea University. First of all, I'm going to take a moment to introduce some of the research that I do as a climate scientist here at Swansea Geography. I work on the evidence for the changes that have happened in the past in our climate that are stored in the rings of trees. My official research topic is called dendro, meaning trees, and climatology, meaning the study of climate. I am a dendroclimatologist. There is a huge amount of information about how our climate has changed in the past, stored in archives that include trees, lake sediments, ice cores, peat bogs, all the ways that our planet physically records the way our climate has changed in the past. And that's a real speciality of our department here at Swansea Geography. So what I'm going to talk about today is how we as geographers approach climate change. For a moment, I want you to think about the last time that you saw something in your social media feeds or on the news that was about climate change. It might have been asking you to think about how you use resources in your life, maybe reusing bags when you go to buy vegetables at the supermarket. It might have been asking you to think about the cars that are in your family. Could they maybe be using electric fuel instead of fossil fuels? Maybe you were asked to think about travel and flying. Maybe you were asked to think about eating meat, considering vegetarianism or veganism. You might have been asked to think about plastic, particularly single-use plastic in your life. You might even have been asked to think about whether or not your dogs could go vegan. And at some point, you've probably been shown a picture of a polar bear on an iceberg. Have a think about whether the way that media asks us to think about climate change is actually about science. It's not. We tend to think about climate politics before we think about the scientific basis for climate change and the evidence that we see around us. And that's one of the real problems with conversations around climate change. When we start to think about how our planet is changing, we want to start with understanding the physical scientific basis for how you can change the temperature of the surface of the Earth. Our planet is a big ball of rock and water floating in space. It's actually remarkably difficult to change the temperature of the surface of the Earth. And that's the question that we ask ourselves as geographers when we think about the physical basis for climate change. The only ways to change the temperature of the surface of the Earth are all visible in this picture, and we're going to look at them one by one. There are only three ways to change the temperature of the surface of the Earth. We can change the amount of energy received, the brightness of the sun and the distance from the sun. And those variables change on very, very long time scales over tens of thousands and hundreds of thousands of years. And it's those changes in the amount of energy received from the sun hitting the surface of the Earth that control processes like the glacial cycles. The other way to change the temperature of the surface of the Earth is to change the amount of energy that is reflected back to space, and this is known as the albedo effect. The other way we can change the temperature of the surface of the Earth is by varying the way that energy is trapped and recycled within our atmosphere, the greenhouse effect. Let's look at these. Changes in the amount of energy received from the by cycles known as Milankovitch cycles, and you can do some independent research to learn more about those. Broadly, they are about the relationship between the Earth and the sun, how distant we are from the sun, and how much energy is received at different times of the year by the different hemispheres on the Earth. Albedo. The albedo effect is all about how reflective the surface of the Earth is. White surfaces, like snowy surfaces and pale landscapes, reflect a lot of energy back to space. Darker surfaces allow heat energy to become trapped on the surface of the Earth and raise the temperature. That albedo is heavily involved in processes of climate change around deforestation and urbanization because it changes how reflective the surface of our planet is. The third process is the greenhouse effect, and we're going to look at that in a little bit more detail. The greenhouse effect is a natural process that controls the temperature and the stability of temperature on our planet. It is essential for life on Earth. Climate change from anthropogenic means is all about enhancing the greenhouse effect to a point where too much energy is trapped and recycled within our atmosphere and not enough recycles to space. You've probably, unless you are studying physics A-level as well as geography, never seen this diagram before. Think back to the picture we showed at the start with a polar bear on an iceberg. If we want to start a conversation about climate change, this is the kind of image that we want to start with, because we want to think about that greenhouse effect. Why do some molecules retain energy in our atmosphere and others don't? And that requires an understanding of the physical shape of different molecules. On the left of the screen, you've got nitrogen, which is not a greenhouse gas. In the middle of the screen, you've got water, which is a greenhouse gas. And on the right-hand side, you've got carbon dioxide, which is also a powerful greenhouse gas. You will see immediately the water and the CO2 are what we call triatomic molecules. And that means that they have a very specific relationship with infrared radiation that nitrogen does not. When triatomic molecules meet infrared radiation radiating back from the surface of the Earth, they wobble. And when they wobble, they take energy in and release it back. But they do not release it out to space. They release it in any direction. And that infrared radiation coming from the surface of the Earth is then trapped within our atmosphere. The shape of molecules determines whether or not they are greenhouse gases. And if you want to read more about that, you can investigate triatomic molecules and something called dipole moment, which will let you understand the wobbling that is all important when we try to understand the greenhouse effect and the physical scientific basis of climate change. There's that wobbling in action. And it would be very unusual for us to think that we were looking at climate change right now, but actually this diagram is showing us why enhancing the greenhouse effect is so problematic because of the way these triatomic molecules wobble when they meet infrared radiation and the way that recycles and traps energy within our atmosphere. So let's think back to our picture in which we can see the energy as the heater of our planet. There is a little bit of residual heat retained in radiation in our planet, but most of our energy comes from the sun. We can see the albedo effect and we can imagine our atmosphere. Let's think about which of those processes controls the long-term temperature change on our planet. When we look at this picture, we can see those three processes in action. We can see the sun that controls the majority of the heat that we receive on the planet. We can see the albedo effect in action in the difference in colour between our bright snowy surface reflecting energy back to space and the darker rocks which will trap energy. And we can imagine those greenhouse gases and non-greenhouse gases in our atmosphere. As geographers, we look at these three processes and think which of them can be controlling the long-term temperature changes on our planet. And the sun is very important here because when, as geographers, we look over long time scales, we realise that actually temperature on our Earth over billions of years has been surprisingly stable despite huge changes in the amount of energy received from our sun. In the distant past, our sun was a faint, young star, and it only emitted a small amount of radiation. Despite that, millions of years ago, there was evidence for the temperature on the surface of the Earth being suitable for life. And what that tells us is one of the processes that we've discussed must be a long-term thermostat for our planet. There is one of those processes that controls the long-term temperature variation on our planet and keeps it stable. As geographers, the reason we need to understand this because it tells us why enhancing the greenhouse effect is so dangerous. And that process is actually the long-term carbon cycle. It's rock weathering, effectively, that keeps us the right temperature over long timescales. When energy from the sun reduces because of one of those Milankovitch changes that we talked about, our atmosphere cools down, and rock weathering, one of the most important geographical processes there is, slows down because of that reduced incoming energy to our atmosphere. This means there is less carbon dioxide dissolving into rainwater and getting laid down in deep sediments, and more CO2 remains in the atmosphere. Over long time scales, that allows the greenhouse thermostat to kick in and correct the temperature change and warming our Earth up again. And that is why, despite over very, very long time scales, millions and billions of years, when the energy received from our sun has changed quite dramatically, the temperature on Earth has remained suitable for life. The greenhouse effect and the rock weathering part of the carbon cycle is our Earth's thermostat. And when we interfere with it, we cause dangerous climate change. So an important thing for us to remember when we think about the physical and scientific basis for climate change as geographers is that the greenhouse gas is a natural process that keeps Earth's temperature suitable for life. We have enhanced it by releasing additional fossil fuels into the atmosphere, resulting in the dangerous climate change that we see now. I'm just going to end this short video by showing you the climate stripes, and I would encourage you to research climate stripes for a bit of work. This is a visual method developed at the University of Reading by which we can see very clearly the changes in temperature as observed from thermometers all around the world that show us how our planet is warming through the 20th century and through the 21st century. Thanks so much for listening, and watch out for more videos about climate change. And don't forget to check out our new degree scheme in environmental science and the climate emergency. Thanks for watching.